All right, so my intention is to talk about consistency today, but there are two small pending issues I want to tackle. It's two questions raised by two of the students in class. Let me first talk about them, and then hopefully we gain some speed, and we can move on to consistency. Okay. So the first one is an interesting feature in VMware virtualization software. The issue was, if we want to checkpoint, remember checkpointing, replication, all of these things are tied together, right? So an interesting issue is, can you take a snapshot of the entire state of the system? And the idea was that's going to be something quite costly because of the large amount of memory you have in the systems now. So in principle, you should essentially save everything that's in memory. But to a large extent, that might not be necessary. Okay. In particular, what would be nice to actually save in some sort of parcel checkpoints would be only things you know for sure changed. Okay? And if you make that set as small as possible, I mean, only things not you know for sure changed, because that's hard, I'm sorry. Only things you're aware of that might have changed, but you have to make that set as small as possible. Right? Now, ideal situation would be you even watch particular independent memory locations and you only save the memory locations that got actually changed. Of course, that's going to be impossible. Too many memory locations. Algorithms would be extremely slow to even determine what changed or what didn't change in that way. Okay? To some extent, that's what the garbage collector does, but only while it runs in memory. But it turns out that there is an interesting mechanism that's built deep into the virtual memory system that allows you at the page level to determine if something got changed or not. Right? So very, very briefly, remember the page system. And these are all tricks that can be used in order to reduce the amount of work that needs to be done for some of these activities, including replication. Right? So virtual memory system, if you remember, it's a virtual view of the memory. There is there is a multi-level translation table from the virtual memory to the physical memory corresponding to each process in the system. And somewhere here we have the physical memory. This is the physical world, and this is the virtual world. Right? And essentially, I'm not going to draw the entire 3-level or 4-level table that does the translation. There is some translation between the location of this virtual page to the physical location of this memory. But there is more to the virtual memory system, which I did not tell you about. Right? Namely, writes about the pages, and also information whether the page got changed or didn't get changed. Now, this information can actually be crucial because the operating system itself has to do optimizations while it runs. When it has to flush things on the disk in the swap area, you would rather flush things. You need to determine whether the content of the page got changed, in which case you have to save it in the swap. Or if it didn't get changed, you might already have it in the swap and you don't need to put it back. Right? So one piece of information for each of the pages maintained is if it's dirty or not, if it got changed. That's one of the issues. Another interesting mechanism is something called copy on write. And this is an essential mechanism in order to speed up starting new processes. So a particular problem, for example, when you fork a process, so you have now two processes versus another, is that you have to go and copy this very large table, right, that contains the mapping between the two tables. I'm sorry, between the virtual memory and the physical memory. And that in itself, it's a little bit of a disaster. Most of the time you spawn off another process just to run a little external command. And if you're using 128 gigs of memory, your table might actually be enormous. Right? So you run in all kinds of trouble if that's the way you do it. But there is another essential mechanism. And by the way, these mechanisms are fundamental. Right? So you really need to know about them, and potentially similar things can be emulated in completely different circumstances. Right? So you want to keep track of dirty pages, or if you want dirty objects. So dirty objects are objects that got changed. It's the only ones that you should in fact save. And the other one is this copy on write. So the copy on write refers to the fact that you set yet another bit saying, you know what? Let's keep things exactly identical in the two processes. But whoever needs to change it first, instead of reflecting the change to everybody, which is undesirable because you really wanted them to be different, what you want to say is create a copy, but only of the page that actually got copied, got written into. Right? So initially the page was read-only, right? And it's in fact marked as a read-only. This is how the copy on write mechanism is implemented. when somebody tries to do a write into it, you have multiple processes now pointing to it. When somebody tries to do a write into it, let me designate the write by a capital W, then essentially there is an exception fault generated deep inside the architecture. But the operating system remembers that this is a page for which it wants to do copy on write. So instead of bothering the program and saying, hey, segment violation, one or another, it says, you know what? What I'll do is at this point, I'm going to, in fact, create a copy of this page. So this is the original page. You create a copy of the page. And you change the table only for the process that actually tried to write. And you change the writes to this, so it actually has the write. It can actually write. And of course, then the hardware is going to reissue the instruction that tried to do the write. Now, the interesting opportunity here is to remember the pages on which you were, in fact, forced to copy, because those are the pages that changed, right? So you don't really need to go and look at all the variables that the program was changing. You're just watching which pages are copied using the copy on write mechanism. And if you remember that, that's really a delta on top of the previous state that can be applied to recover the new state of the system, right? If you're in a situation where most of the time you're just using information that's already built throughout the memory and you're not changing too many of these things, and that turns out to be the case in most situations, the amount of information you, in fact, need to save to be able to safely recover the state is much smaller. Okay? So these are so-called incremental updates, or the checkpointing technique is called incremental checkpointing. Incremental checkpointing. But I want you to remember something crucial about this. You need a hardware mechanism to detect what changed, right? If you really need to go and compare something or do something through large amounts of memory to determine what in fact changed, it's a disaster. You don't want to do that. You're better off by just saving everything. If you need to scan the entire memory to find what changed, you're better off probably by just saving everything. If you have this kind of hardware support and you can memorize which pages in fact got changed, for example, this copy on write mechanism, right? This could become a feasible alternative, okay? Now, possibly something similar could be used to implement something that we did not discuss, which is distributed shared memory, right? Distributed shared memory refers to the fact that I want changes in the local memory on one machine to get reflected into remote changes so that I give the illusion that they in fact share the memory, right? Now, shared memory is out of fashion for many years. It's still used in high-performance computing, right? But it's out of fashion in distributed systems for many years because it turns to be too much of a low-level mechanism that's too hard to implement, right? You need to know too much about the application to get some reasonable performance out of it. But if you would want to implement something like shared memory, distributed shared memory, then essentially a copy on write mechanism is crucial. You don't want to bother any other site that's supposed to show the same content of the memory, right, until somebody tries to write, because the reads are much easier. So we're going to see that today, later in the class, right, when we talk about replication, because the same kind of core issues will pop up. Reads tend to be easy. The writes are the ones that create problems. So keeping track of the writes, and in particular the order of the writes, right, that's the big tricky issue. Of course, distributed shared memory is still very complicated, right? And in order to, sorry, you also have notions of consistency when it comes to distributed shared memory. They are very hard to enforce. It's a complicated issue. This is why distributed shared memory as a mechanism, it's completely out of favor. Okay? All right. So this is the first issue. And apparently the new version of VMware is using this kind of tricks to significantly cut down on the amount of stuff it needs to write to the disk. That essentially means what? Faster checkpointing, which means faster smaller amount of time from the moment you click save to the moment it's saved, right? Otherwise, for some of the large virtual machines, it can literally take a couple of minutes to save the state, which is highly problematic if the power goes down or any other issues, okay? All right. Good. Now, let's talk about the other issue that's related to random number generation. I promised you long back to discuss this issue. It's something that looks very simple and benign, and we use everywhere, but turns out to be extremely problematic in distributed systems in general, and basically multi-core systems in particular. Okay. Depending on what is it that you want to do with random number generation, right? It could be devastatingly bad if you if you make an assumption that looks like a reasonable assumption in the global system, then it becomes extremely bad. So let's talk a little bit about what goes in there. It's important to know about this particular issue about random number generation because it in fact kills performance. It will kill you faster than anything else on multi-core systems. And let me explain why. Okay. Especially in large simulations, and most definitely Scala has this issue. Okay. They all have this issue unless you build a very, very special mechanism to go around it. And we are going to find a mechanism together, in fact. Okay. So very short introduction to pseudo-random number generation. I mean, why is it pseudo? Because we don't have real random numbers. Okay. Well, we kind of do, but the devices are expensive, and then you would require absolutely all the computers to have access to an external device, and then it's kind of tricky. Not to mention that you cannot really write very natural programs. You have to keep on calling special functions that have to go through the kernel to get a random number or to get a pool of random numbers, right? So it can get problematic, even with real random numbers, okay? Now, the vast majority of programs that use random numbers, in fact, use pseudo-random numbers. Okay, let's talk a little bit about them. So, pseudo-random numbers. So why are they called pseudo-random numbers? Because they're not really random numbers. They are just simulated to look like random numbers. Okay. Now, there are basically multiple issues with pseudo-random number generation. One of them is how good a pseudo-random number generator is. But I'm not going to discuss that much. I'm going to discuss the common property of all the pseudo-random number generators, the fact that they use state and state transitions. Okay? So the high-level idea of virtually all pseudo-random number generators is the following. I have a state which it's either small or possibly very large, depending on how sophisticated your pseudo-random number generator is. Okay? And the quality will really depend on how large the state is and the state transformation. And in fact, what you want to do is do the following kind of process. Okay? You're going to apply one function to produce the random number, and another function, let's call it capital F. They are usually very related to each other. Another function to update the state. So the way any random number generator, pseudo-random number generator works is from the current state you extract some scramble value through this function, and that's what you return. At the same time, you apply another transformation to the state, which is usually some kind of a shift, some kind of a modification to the state, and you have to apply it back to the state. So that next time, when you call the random number function, again, you produce something looking scrambled, and you create another number. Now, this is precisely why if you initialize a random number generators with the same starting point, with the same S0, with the same seed, the S is called the seed if it's used as S0. If you initialize the same random number, pseudo-random number generation algorithm with the same seed, you're going to produce the same sequence of random numbers, right? Good. So that's a nice property. And it's a nice property. Why? Because it still allows you to do randomness, but if you find problems, you can reproduce the problems by essentially putting the same seed. And you nail it down and basically say, hey, put the seed this, and you're going to see that the problem exists there. So everything is nice and dandy, and it's great. Okay. All right. As long as you have a sequential program, right, then there is no problem whatsoever. Whenever you write rand of something to call this function, right, this entire process happens. A new value is computed. The state gets updated. And if your program is sequential and goes through the same sequence of states, you are going to have the same sequence of numbers generated. Okay? The trouble starts when you use this in a multi-threaded environment. So let's see what happens in a multi-threaded environment with this. So threading. Right? So what's the problem with multi-threading? Well, I have a state, and I'm going to have multiple threads calling the random function, right? So when they tell you that a certain library is thread safe, what they mean is for situations like this, threads don't step over each other. So how would you make this thread safe? Lock, right? Mutual exclusion region. This is exactly what mutual exclusion regions were really designed for. Okay? So the way to make this random function thread safe is to do the following. For every random number generator, you have a different lock. So you're going to pair the RNG with a lock. Essentially, you can extend if you want the data structure or whatever. You put it outside. It doesn't matter. And in fact, every time anybody wants to use the random number generator, you apply the random number generation, which needs to update the state, and then unlock. Right? Now, you see what the problem is? Well, the problem is all of this locking. So imagine that you do a large-scale simulation. In the simulation, every thread calls random number generator rand to take tiny decisions about how to move something around and do things around. So it looks like they all work in parallel. You have 32 threads, let's say, which is now relatively easy to acquire. 32 threads, they are all running, and you say, hey, I should run about 32 times faster. In fact, it's going to be a complete disaster because of this lock. In the vast majority of the time, they are just fighting over the lock of the same random number generator in order to provide you with the random numbers. Right? You see how it is? And it's completely hidden from you because you never call lock. You call the library function that's called rand. The library function only says, I am thread safe. OK. And you say, oh, being thread safe is very good. You call it disaster from a performance point of view. We've been in a situation like this, right? When we try to do some simulation in the data processing engine, right? If you don't have this kind of things, it runs very fast. You call this, and the strangest thing happens. And let's explain a little bit what's going on in there, right? The strangest thing happens in the following sense. You know you fired up, let's say, 32 jobs. You fire them up. You even put log messages when you fire them up. You look at the CPU utilization, and the CPU utilization is 2.1 to 2.5. Right? So you literally go on top, and it says, OK, 2.5 out of 32 cores are used to do processing. You have absolutely no sleeps in your code. It's supposed to just go continuously. What goes on in there? Now, this is the kind of stuff that you're just puzzled, and you say, hey, something is broken in the OS, and it doesn't report correctly the running time. No, it reports correctly the running time. Actually, the effective running time is much worse than 2.5. Okay? So what goes on in there, it's exactly what we were discussing in the context of distributed systems. The way these locks are implemented is essentially, some mechanism to make sure that not two processes, not two cores can go at the same time through it. And a waiting queue. Okay? Most of these locks, in fact, use a waiting queue, not a spin lock. A spin lock, we just basically make the processor run very hot and still not make much more of a progress. And essentially what's happening is most of the 32 guys that are supposed to work at the same time, they're just in the waiting queue to wait for the lock. Right? One of them gets out, it barely does any work, and other guys immediately jump in and do. So you're kind of running on two cores and a little bit more, but even those guys don't do much work because immediately they will lock back in. Right? The slowdown, if you use this, is going to be at least a factor of 30. Which now sounds paradoxical, because if you do very little work with the random number generator, right, which is quite likely because you're going to use it all over the place to take all kinds of random decisions, right, you might actually be better off by not using threads at all and just running in a unithreaded system. As strange as that seems, a complete disaster from that point of view. How do you remedy this situation? Now, whatever we do to remedy this potentially can be used to solve other problems in distributed systems. So the issue is a common state. You have to get rid of the common state. Actually, ideal situation is to get rid of the lock altogether, so you don't even lock even when there is no contention, because there is a little bit of a price for that as well. Right? So how do you do that? Well, ideal situation would be this, and you have to be very careful what this buys or what this doesn't buy. You need a thread private random number generator. Okay? You still want to use some mechanism like this, because it's our best way to generate good random numbers. And by the way, if the state is decent here, if you use the random number generator in Windows, it's a complete disaster, by the way. It's only 16 bits. It reports 32-bit numbers or 64-bit numbers, but it's 16 bits. Why? Backwards compatibility with Windows 16, right? It's just, on Windows, don't ever use the random number generator provided by the standard library, okay? In Linux, it's a little bit better, but not much better, okay? Get a better implementation of the random number generator. There are lots of libraries that do this, and simply don't use logs, but you need a separate one for every thread, which ends up being a little bit tricky, right? Ends up being tricky because you either have to in fact, treat the random number generator as some sort of an object that needs to be created before my computation when I'm sure I'm in a single thread and I run, and I don't spawn off threads anymore, right? In which case, I treat it as an object. Now, that is reasonably doable, especially if you're implementing something like C++ or whatnot. Or you have to use a mechanism which is supported now by some of the C++ compilers. By the way, if anything gets supported in C, it has a decent chance to make it through the hierarchy to the higher level languages, right? Or you use a random number, you use so-called thread private data. Now, the new C++ compiler supports something like this, right? It's called thread private data. And essentially, a new copy is created for every thread. And the compiler deals with that, how it does it. And right? It can't be on the stack of the thread. It's a separate area allocated by the standard library that's only for each of the threads. And the mechanism, it's quite complicated, but it doesn't quite matter. Now, if you do something like that, if this is really a thread private, you lose some and you gain some. OK, so let's see what we gain. We gain the ability of running without a lock whatsoever because it's now a sequential program. There is no reason to do a lock at all. You might maybe do some sort of a lock at creation, but even that, it's probably not needed. OK? Which means this problem disappears completely. I mean, you should be running 30 times faster, 32 times faster, whatever. OK? And you can actually try this. What you're losing, it's kind of very subtle, and it's not clear that's a big loss. OK? So the warning here is the following. Sometimes what you lose is not even that interesting, and you shouldn't have clinged to it, okay? Because it wasn't exactly what you wanted in the first place. Okay, so let me explain. So what you're really losing if you run each of these guys on independent threads is the fact that another guy calling the random number generator influences yours, so your numbers are more random, maybe. So you think you're losing this, but I'm going to argue that you lost it anyway. Right? The ability to make the program completely deterministic by picking a seed. Okay? So it turns out that these things are completely deterministic if you select a seed, if you are single-threaded. Okay? But I'm going to, so you might think, hey, if I use it in thread private data, then each of them, I mean, by the way, a complete disaster would be the following: to pick the same seed to initialize all the thread random number generators. Right? And that's going to produce strong correlations between what the threads do. Potentially, all the threads do the same work. So you work 32 times faster, but you do the same work, and you're going to have arbitrarily weird results. So one crucial thing you're going to lose is this. You can't specify a seed and have the same seed for everybody. You have to move a little bit. I mean, you have to derive a subseed from the seeds with some randomness that's separate for each of the threads. Maybe the thread ID or whatever, or just give up on the random seed, on the initial seed. Okay, so it looks like you lose the ability to play games with put the seed at a certain value and reproduce problems. But I'm going to argue that you lost it anyway. Why? Because you see, the thing you can't control is the specific interleaving between calls to that function of various threads. You can't control that order. You simply cannot. Locks or no locks. So many things influence the speed at which progress is made in different threads. Nothing is really synchronized with anything else. Even the clocks at which the cores run, it's a little bit different. One of them will get a little bit sooner than the other one. And anyway, on top of whatever happens, even if you initialize it with the seed, you're not going to get deterministic behavior, right? So the moment you talk about multi-threading, you might as well forget about deterministic behavior for the most part. So the behavior was non-deterministic to start with because the actual interleaving, who uses what values at what time, were different. Which means you're going to have errors that are hard to reproduce, or they go in a different way to start with. This is a major problem with any algorithm that uses multi-threading. And it's only amplified when you do true distributed systems, right? So initial seed was gone anyway. If you switch to a solution that has no locks, you basically just acknowledge that and say, hey, I give up on any of that thing. Now, you could make actually things potentially more reproducible per thread, because now you could do maybe a separate seed, as long as you can control the seed per thread, right? It depends on how sophisticated the library that you use is. If you can control the seed per thread, you could make them now be, in fact, deterministic because they don't share the random number. Okay. Now, the reason, again, I'm going through all of these details is it's a completely hidden problem. I believe a lot of people bumped into it, and they just don't know, and they have really bad performance, right? So whenever you use random numbers in any circumstances, ask yourself the question, am I close to this? I mean, what random number generation library am I using? Usually you don't care. You say, people that implement this kind of things are gods. They know what's best for me. I shouldn't even think about it. Well, it turns out that that's absolutely not the case when it comes to this. They're way, way, way behind, right? They just made everything thread safe. Now, thread safety, it's about not having the program crashing, not about ensuring performance, right? So just keep this in mind. Not to mention, you should always question what random number generation you use, because there is such a vast difference between the random number generation. You can get very weird behavior with bad ones, right? So, yes?
If I use the same seed, it will generate same sequence each time.
If you do not have multi-threading on the random number generator.
But if we have multi-threading, can we use the same seed to generate any sequence, for example, sequence of n numbers, and for each number in the sequence can be used as a seed for a thread?
So, look, sky's the limit. You can do anything you want, right? So this is essentially the issue raised was, can I derive seeds, the per thread seeds, from a general random number generator? Yeah, but by the way, there are better ways to do it. So here is an interesting question, okay, which is another hidden problem, right? So by the way, if you do not initialize the seed, what do you think happens with the standard library in random number generation? But you see, that's where the problem is, okay? If you don't start asking these questions, of course it will have its own seed, but that doesn't mean it's good, right? Do you see what the difference is? The difference between works and is good, and I know what it produces a certain quality. When it comes to simulation, it's crucial to know what's the quality of the random numbers you're getting. It's not a problem to use pseudo-random numbers. The problem is not to know how good your pseudo-random number is. Well, the library will actually initialize it at the same value, at 0. Okay? Which means you get always the same sequence of random numbers. You probably have noticed this. It's like, wait a second, I have a random program that runs in the same way if it's sequential. If it's not sequential, it doesn't quite run in the same way. Okay, whatever. All right? So how do you initialize random number generators? Well, yeah, I mean, time is a reasonably lousy one, by the way. Okay. Yes, so time it's a lousy one, I can go into details, but somebody said a hardware random number generator. Okay, so I just argued that we don't have a hardware number generator, but I actually mildly lied. Okay, it turns out you can in fact build a hardware number generator. It's just the problem with it is going to be that it's very hard to get a lot of random bits out of it, but you can get some random bits, right? So imagine I have a hardware random number generator. I can't get too many bits out of it, but I can get a decent amount, right? I could use it, that's perfect, to use it to, in fact, initialize all the seeds, right? And then any per thread such random number generator that I build will just go and bring from the pool. But the pool, the trouble with the pool, I'm going to describe where the pool comes from. The trouble with that pool is you don't have too many bits growing in there per unit of time. And when you run out, you have to wait until they grow there, which is a disaster, okay? But if you only get seeds, I mean, even if you get seeds of 256 bits or whatever, it's going to be more than enough. So let's think about this. We have something that we believe is a deterministic machine. How would we get some randomness? From where would we get some randomness? Now, forget about the how. Just think about what. So in order to get randomness, you need to have random events and measure something about the random events, and then use the measurement to do that.
Power?
How would I use power?
The temperature of
No, that's some, I mean, that's kind of something. Temperature is not, okay, fine. So I give you this. We have temperature sensors on every machine. Good, so I could use temperature sensors. Okay, what else? I'm sorry? Right, so we need anything that we suspect is at least a little bit random. Now, I want you to understand that it doesn't have to be fully random. Just the decimal points to be random and we are fine. For example, so we can do badly or we can do well with a temperature sensor. So what I mean by that is, if we really use the actual value of the temperature sensor, it's not so good. but imagine I can measure the temperature sensor with 4 decimal points. A perfect candidate for a reasonably good pool of random numbers is just the decimal points and not the temperature itself, right? So if the temperature, and by the way, that is the case because most sensors at least are going to produce some sort of a number there, and then you have to cut it down when you present it to the user, right? So imagine the temperature sensor. It's a 32-bit sensor. By the way, what's all these bits about a sensor? Well, it's basically the number of levels it can discern. Not perfectly because it has noise and it has things, but that's perfect in this situation, right? So if this is a 32-bit temperature sensor, I could say, you know what, let's not be greedy. Let's use only 8 out of the 32 bits, the insignificant ones that are likely to be the most erroneous, the most noisy. I'm going to use 8 bits to mix them into whatever I'm going to do for random number generation. Okay, so that's one source. Another one is precisely timing things that can't possibly take the same amount of time. For example, the amount of time it takes a hard drive to respond. Hard drives are notorious for how slightly unreliable they are with respect to actual timing events. But you can measure the time very accurately in an operating system, right? We talked about the time measurement before. So if I now measure the time, but instead of measuring it in milliseconds, I could measure it in microseconds and keep, again, only the decimal points. So you can do all of these kind of tricks, right? So timing events. You measure the timing. You don't keep the big part because you know that's going to be in a certain range, not going to be particularly random, but you keep the decimal points. It's the same idea. You keep only the insignificant digits. Right? So you can pile up all kinds of events that happen in the kernel. Keep the part that you believe is going to be reasonably random because it's just measurement error, right? And try to extract from that random numbers. It turns out that, I mean, this is again a situation, one of those don't do it at home situations. Don't bother to implement your own random number generator like this. It's complicated. It needs quite a lot of theory. How do you guarantee that you get decent random numbers, you're not biased, and so on and so forth? Good thing for us is the Linux people implemented a very nice mechanism to produce such random numbers, right? And is /dev/urand. Or it's called random, I think. Right? Do you remember the name?
Well, urandom is pseudo-random. Random without the U is
Sorry. Random. Thank you. OK. So /dev/random, it's going to be essentially access to the random number pool that the operating system maintains by doing all of this timing and God knows what else. They keep on changing what exactly they measure and how they do it. The thing to keep in mind is, the good thing is it is random. It's not pseudo-random, it's random. The bad thing is it's slow. It's not slow in terms of how fast it reacts, even though that's kind of slow because you have to go in the operating system. It's slow in the sense that if you run out of what the OS believes are random bits, it has to wait until enough events happen to give you random bits. So if you read enough from it, you're going to exhaust the random bits, and it just blocks until it has such random bits. Right? So then your program will have 0 CPU utilization because you use the /dev random too often. So it's good for seeds. It's bad for almost anything else. Okay, so that's the thing to have in mind. Okay, and interestingly enough, it's actually mapped through it's some sort of a virtual device. Right? This happens all the time. We talked about that. It's implemented through the virtual file system. It's yet another virtual file system trickery. Okay, to get stuff done. Okay. So possibly the winning combination for random numbers would be the following: you get the seed from dev random for each of the threads when you start the thread. You have a completely independent implementation for each of the threads, and you use a good algorithm. In here, Google for them. They're extremely well studied. Okay, I'll mention in a second what properties they must have, and use that on top of the random thing, and then you get a good quality pseudo-random number generation. Okay, so just briefly to mention what's the difference between a good and a bad one. And by the way, there is a research area dedicated only to this. Okay. And by the way, this is related to cryptography to a large extent. And in fact, a lot of security holes in cryptographic systems are related to how the random numbers that create the random keys, supposedly random keys, are generated. Because any defect in the random number generator can actually be exploited. So it doesn't matter how many bits you have in the key. What matters is how you generate those bits. Okay? So one specific problem for random number generator is if they produce correlations or if they have very small cycles. So all pseudo-random number generators have cycles. Okay? That means if I keep on applying the function again and again and again and again, eventually the sequence is going to repeat. Right? How long that cycle is, it's a property of the pseudo-random number generator, and you can guess that the longer the better. Right? Well, a bad one would have the sequence repeating. Right? So let's suppose the random number is 32 bits. Right? I mean, a truly bad one will have a cycle of only 2 to the 16, and that's basically what happens with the one on Windows. But 2 to the 16 is a disaster. You essentially get only 65,000 and something different values, and they repeat afterwards. A reasonably bad one is to have a cycle of length 2 to the 32. Right? That means after that many values, you're actually repeating. Now, the sequence looks reasonably random, but they repeat, and that's not good, because that will create other problems, which I'll mention in a second. Now, some decent random number generators here will have cycles that are way bigger than the life of the universe. So you're never going to see a repeating sequence. Okay? Way, way, way bigger than this. I mean, they can reach easily cycles of size 2 to the million or 2 to 10,000 at least, some decent ones. Okay? All right. Another thing related to pseudo-random number generation is if you look at, let's say, I don't take only one value. I take, let's say, 10 or 5 successive values, or 5 values at any point. The question is, how correlated are the 5 values? Now, if it's truly random, they should not be correlated at all. You should not have any correlation whatsoever. I mean, other basic properties are, if I take random numbers, are they biased towards one end or not? They should not be biased. They should be perfectly balanced, right? So if the number is between 0 and 1, the average, if I take average of such values, I should hit 0.5. So expectations should be 0.5. But also, they should not have correlations. Well, you see, if the seed is very small and the mechanism doesn't use a large enough seed, you will start to get correlations that could create subtle problems which are extremely hard to have a grasp on from a theoretical point of view. If you have a little bit of a correlation in the pseudo-random number generation, it's very hard to say what they would do. It might do nothing, or it might introduce subtle errors in your simulation. Okay? So this is why I strongly recommend you Google and you find one that looks good rather than inventing your own. Never, ever write this kind of function and this kind of thing for the pseudo-random number generation. Okay? Now, there is a very interesting opportunity, and I'm going to talk about this when I talk about security, to produce extremely good random numbers right now, right? With none of these things and none of these big seeds, and actually fast. And I know of nobody who uses this mechanism. Okay, so you're maybe not the first, the second, because I mentioned it in the database implementation class last semester. Okay, so here is an interesting opportunity. So think about a random number. What's the ideal situation for a random number? If it's truly scrambled, you'd see no relationship between the previous value that produced by a random number and the next value. Ideal situation is if you would know for sure that's impossible to tell, to go from one value to another. So you can actually put a number of restrictions on this, right, that go beyond just requiring them not to have correlations. It even things like, so imagine an adversary, it's watching the sequence of random numbers that come out of your random number generator. Could they determine the seed? By the way, if you determine the seed at any point and the machine is deterministic from that point on, you in fact know what the random numbers are. So imagine, for example, that they would use a not so good random number generator for the lottery, right? They use the machine for the lottery only for the official mechanism to get the random numbers. They move to computers because it's cheaper. But they never touch that machine. They never, okay, so you know. Or even if they touch it, you kind of know something about that thing. If you can actually predict, if you could compute the seed, you could actually perfectly predict the sequence of random numbers, which means you are going to win the lottery over and over and over again. Not good, right? So you can pair up pseudo-random number generation with also some notion of security. Can I make this pseudo-random number generator in fact secure? Okay. The lottery better make it secure. Well, one trick there might be to use a physical process, right? Maybe one of the special cards. This might, I wouldn't even trust this for a lottery that has the pool at whatever $100 million or something, right? The Powerball it climbs up to a large amount. You really want to put a lot of sweat into the random number generation there, okay? Right. But this actually creates an interesting pairing with security. right? And potentially with encryption. So a particularly intriguing idea is to generate random numbers using encryption techniques. Okay, so what do we know about encryption, especially, we are going to come back to this later, especially about symmetric ciphers, right, like AES 256, which is kind of now the de facto super strong standard, right? Advanced encryption standard 256. This is basically a symmetric encryption method that uses keys of size 256. And it's, well, it has variants and whatnot, but it likes to work on blocks of 256 bits, right? What we know about this is even if I give you an enormous sequence, I mean, forget about sequence because it's not clear what I'm encrypting, but even if I give you a very large number of clear text and encrypted text, you can still not derive the key, right? It's known to be extremely secure, right? So I think now it's somewhere around this, but even if I give you more than 2 to 200 such pairings, you're not going to derive the key. That, in fact, makes it an ideal candidate for random number generation, okay? How? Well, here's how, okay? Instead of having that, you do something very different, okay? The input is going to be the sequence, 1, 2, 3, so on and so forth. You pick a key, a random key. And in fact, you use AES 256 plus your key to encrypt the sequence 1, 2, 3, and whatever you want. What comes out at the other end, and you can do this incrementally. You can just, because it's a block algorithm, you just say, OK, increment the next number, increment the next number, increment the next number. OK? Remember, it's the key that's different from each of them, right? It's the same as the seed. But what comes out of it, it's something called cryptographically secure numbers. OK? That essentially means that even if you know that you encrypt 1, 2, 3, 4, right? You look at the sequence, you're not going to be able to derive the key anytime soon. OK? Now, why is this interesting? Well, this is interesting for a very weird reason. Normally, you would not do something like AES 256 because it's likely to be a much more elaborate algorithm than any of the algorithms that are designed for this. So normally, you say, you know what? I'm going to use other algorithms. They are known to have strong enough properties. It's not quite cryptographically secure, but that's fine. But will run faster than AES 256 that needs about, I think, about 16 stages. Or no, they use 32 stages now. Okay? But here is the kicker. This, it's implemented in hardware. Okay? So what that means is, in the new generation of AMD processors and Intel Xeon processors, they introduce special instructions. Right? And this, in fact, runs faster than almost any other random number generation here because it's done with transistors in hardware. Right? So this is kind of a golden opportunity. So when you go in industry and you need random numbers, and you know for sure that you're going to run on machines that are reasonably new, by the time you graduate, everything is going to fit into this category. Okay? Then you say, people are going to say, yeah, this random number, forget about it. AES 256 in hardware. Right? Done. That's my random number generation, right? Now, this thing gets so good at random numbers that you can, in fact, tell if on a hard drive you have encrypted data by looking how random the data looks. If it looks random, it's encrypted. It's now easy, in fact, to tell. I mean, it's not easy to decrypt, don't get me wrong, but it's easy to tell if you have encrypted data on portions of your hard drive. You just do a test of how random it looks. It looks very random, it's encrypted. That's it, right? So keep this in mind. And this is a really, really big thing. It's going to be very secure and very fast because it's done in hardware. To give you an idea how fast this this AES 256 is in hardware, I remember numbers in the order of 2 gigabytes per second per core at applying this. Right? So you can produce billions random numbers per second effectively, or close to billions, 500 million random numbers per second. That's more than plenty of running anything. I mean, again, no locking, nothing. You just feed the beast and just keep on going, right? And for multi-threading, you could even do a trick like this, right? Instead of numbering them from 1, 2, 3, 4, you simply take the thread number and multiply it by a gazillion plus a random key that you picked, and then you can share the same random key. There is no possibility of any kind of interference between the two. Now, with a normal pseudo-random number generator, that could be problematic because you don't quite know what it does for it. But these are cryptographically secure. You see, if you would find any problem with this, you would be rich anyway and you can give up on writing distributed systems and go and break security, right? Trust me. So you have to start with the assumption that this is, in fact, extremely sturdy. And then almost anything you put in it is going to come out to be right, as long as slightly different things. Get the thread ID and multiply it by something, and you're fine, right? That's just perfect. OK? So does it make sense, kind of what I'm talking about? But this is a very interesting opportunity that nobody mentions. I mean, it would be interesting to write a library like this that uses the hardware-supported AES-256 to produce random numbers. OK. All right. Good. So now it's time to go back and continue talking about what we care about most at the moment, unless you have any questions about that. So sorry, any questions about either this or the other one? Look, for anything I say, my advice is Google some of the keywords to find more of the stuff. Wikipedia helps. General Googling helps. For some of the crazy things like this one, probably nothing helps. But I mean, you can start thinking about your own solution for some of this, right? OK? Copy on write. Google copy on write and see what comes out of it. But it's essentially that mechanism that I just mentioned. OK? Good. So let's go back to consistency. And by the way, this was a form of consistency here. What consistency does the user expect here? Yes?
You told me that some of the random number generators have a lifetime of about millions or millions of
The cycles.
cycles. How do they determine that?
OK, so this is where theoreticians come into place. This is why I'm saying don't do this at home. OK? So it's strange, but we, in fact, have extremely vast mathematical knowledge. And we can, in fact, characterize these things. Right? They have people that are actually paid to study these things. And they've been doing so since the early 1900s for some of the issues in earnest since 1950s, when Monte Carlo was introduced and so on. Right? Again, you can Google also for this, and you're probably going to find the original article. So if you are a researcher in this area, pseudo-random number generation, you, in fact, when you propose another one, you have to prove that it has a certain cycle, it has a certain extra properties. Right? Other properties are, for example, a shuffling property that at least half the bits going from one state to another have to change. Right? So the state transition is tricky. You can't just add 1 and add 2. Right? So basically, that's another standard for pseudo-random models. So it's fascinating, if you want. Start Googling and look at how deep the knowledge is in that area. But the interesting thing is, to a large extent, this completely supersedes everything, especially when implemented in hardware, because now we tie up good random numbers with cryptographically secure. Okay? That's kind of amazing. So with this, you don't even have to think about it, because essentially you say, I'm as strong as AES-256. And AES-256 is weak, then we are all doomed for many reasons, and we have to invent something else, in which case we'll use something else. Now, this is kind of an interesting situation, and I would strongly recommend you pay attention to these things. Okay? There's nothing like hardware-implemented stuff, but the incentive has to be there for Intel and AMDs of the world to actually do such an implementation. Okay? In the case of AES-256, right, if very few people would use it, yeah, whatever, do it in a library. But now, having support for AES-256 in hardware becomes a strategic advantage. You can sell more processors if you have it, literally. Right? So the moment such an incentive is created, that's the time to pay attention to the mechanism, because it's going to be good for you. Normally, this is reasonably slow in software implementations. The acceleration is more than 100 in hardware for this. Okay? They literally have now gates that just do that. They just do AES-256. In a pipeline fashion, pretty much like the multiplication is happening, right? So this is why it's worth paying attention to current trends in hardware. How do I even know about this? This is a highly esoteric thing, right? Actually, if you buy a processor, somewhere on the list of features, they might throw in some support for AES-256, right? But nobody pays attention to lists of features for modern processors. By the way, do you know what your processor supports? OK, /proc/CPU info. On Linux. Go in there, and what you're going to see is a bunch of numbers, a bunch of things of this frequency, BOGO MIPS, and whatnot. And then the list of features with 2 or 3 letter words. And the list of features is something like 10 lines long when you have 80 characters wide. We're talking about almost 100 different little features that the modern processors support. And you need to do a Google search for each of those little things to figure out what it is. So AES-256 is only one of the 100 little features they support, and all of that is hardware support in modern processors. Okay, I'm just pointing this out, CPU info. Okay, good. Consistency. So let's go back to consistency, and let's talk a little bit about consistency. But I want the discussion to be different than the discussion in the textbook. Okay. The discussion in the textbook is distributed system-centric one, in which you assume everything is nice and dandy for one system, and you just want to make it extend the goodness when you have distributed things. But the core of the issue is, in general, with consistency on anything, right? So I mentioned this last time. What does it mean that a sequential program is consistent? Not clear at all. What does it mean that a multi-threaded system is consistent? And the problem starts right there, and you have a lot of the issues hitting you right that moment, right? The moment multiple threads can weave the execution and change the state at the same time, you have to ask about the notion of consistency, right? So, for example, this is equivalent to saying, if we all go and do an activity at the same time, would we get something that makes any kind of sense? I mean, literally, I could do something and you undo it immediately, right? If I need to do a sequence of 3 actions, right? But somebody interferes with me all the time, I'll never finish those 3 actions. So it's a legitimate question to ask when you transition from a sequential program to a multi-threaded program, do I have some notion of consistency that remains there? And then the question needs to be extended to say, when I have a variety of systems that now even have large distances between them, which means large latencies with respect to the activity that goes on every machine, do I still maintain some notion of consistency, right? So for everything else in class, we had reasonably intuitive notions. We had some difficulty, some things there about the physical clocks. OK, that was a little bit hard. Now, when it comes to consistency, in principle, it's like pseudo-random number generation. What you would like is very clear definitions of what it means to be consistent and very strong proofs that certain protocols, certain algorithms will achieve that kind of consistency. So things can get extremely nasty mathematically. And to a large extent, they don't even have complete proofs for some of these things. At the same time, what's happening is the more you insist on a very strong consistency notion, the more you're in a situation where you're going to need an extremely elaborate and slow protocol to enforce such a consistency, right? Selecting the right consistency in a modern system is the thing that can make or break the system, right? Let's go back to the Amazon situation, right? Amazon people decided to have a very weak form of consistency and weave the entire system around it. And this is one reason why their system is so high performance, right? So again, they can sell you items they don't have, and they're going to fix the problem rather than insisting that you should have all the items, right? It can get worse when it comes to items, if you think about it. It's not even so much only a matter of you have each of my individual items, and you can actually perform the purchase. But for example, you can, and it's again a question of what you promise. You could promise people not only that you're going to get them an item if you solve them an item, but in case you don't have an item, that you're going to ensure the fact that none of the purchases will go through, right? So people can come along and say, you know what? And by the way, this is realistic when it comes to, in fact, making changes, and it's at the core of transactions. You come up with a list of things that the system has to do, and the system has 2 choices. It either does absolutely everything that you say, or none of it, or at least simulate the fact that it has done none of it, right? Amazon has absolutely nothing like it, right? So the more, if you want help you want to provide to the user, the closer you get to these higher level notions like transactions, what I just described a second ago, right? The worse it's going to get when it comes to distributed systems. It's bad enough on multi-threaded systems, let alone on distributed systems, okay? So I want to discuss some of these issues, even though the discussion probably is going to be quite long, and we need to push it next week, right? So let's go through some of these desirable consistency requirements, and let's see a little bit what's entailed. Now, and you have this described in the textbook. Distributed systems, people really like to play with lots and lots and lots of consistency notions and propose solutions for them. Now, the fact of the matter is very few of them are, in fact, deployed in practice. Okay? So lots of things proposed in research literature, very few things actually ticking in practice. at one end, and this is done not because of distributed systems community, but because of database community, and you can kind of just round it up in distributed systems, right? We are going to have transaction processing, which in fact is the pillar of modern e-commerce, and I'm going to talk about that. And not even Amazon goes against this. Okay. And at the completely other end, you're going to have something called eventual consistency. Okay. So transaction processing is a very strong notion. Eventual consistency is a very weak notion, right? Let me go a little bit through transaction processing, and especially when things happen in a distributed way, this becomes extremely burdensome. Okay, so transaction processing basically makes the following promise, right? You're going to have the following two kind of primitives. Well, it's kind of free. So you have begin transaction, then operations you can do on the items, which usually mean some sort of a reads and writes on the items. And then you can finish the transaction in two ways, right? You can say abort, or you can say commit. So let me say begin transaction. Then you have all kinds of operations. And then transaction will either finish with an abort or commit. Abort is also known as rollback, and if they are both syntax sugar on the same mechanism. Okay. So why is abort? I mean, abort, rollback, they are the same because the behavior of abort is the following. If you abort a transaction, you have to clean up after yourself and make the system look like nothing ran in the first place. Okay, so this is rollback. Right? You can abort for many reasons. One of them is the user decides that something is not quite good, and you abort. For example, you're trying to move money between accounts, and you just realize you don't have enough money in one of the accounts. You say abort. And then the system does the magic and makes sure that it's as if you didn't run the transaction in the first place. One thing that most people don't understand is that abort, it's actually one of the primary weapons the system can use to ensure that transactions are correct. If it detects that a transaction does not completely abide by the rules of transactions, it has the option of aborting it, right? So if you run in trouble, and there are many ways to run in trouble when you run transactions, one way to get out of trouble is to abort. Now, abort sticks to the promise, right? You can tell the user, hey, for whatever reason I aborted, right? And that's considered to be fine. Well, kind of lost my train of thought. Okay, so let me explain one thing that people don't understand about transactions. So here is what the system does not promise. So even when it comes to transactions, it's very important to understand that you don't have more promises than what's on the board. Okay, so abort can actually be initiated by the system. So the system can say abort, and the user is going to know that transaction abort got rolled back, even though nothing was wrong with the transaction. Okay. This is considered to be fine by the specification and normal. So what should the user do in that circumstance? It can issue again the transaction. Okay. So aborts out of the blue sky are considered to be perfectly fine and actually are strictly necessary to have any reasonable notion of transaction processing. Okay. Aborts are fine. Even when generated by the system. The other one is there is no promise about the order in which the transactions are processed. Okay. No ordering, no transaction. At least overall. Okay. So what that means is if you have two clients that send their transactions, and you say, you know what, I sent my transaction first, why was it not executed? The system does not promise that it's going to run the transactions in any specific order. Any promise the system makes is only with respect to I abort or commit this transaction, right? But not in which particular order I run the transactions. This is with respect to the global view of the system. But that doesn't mean the system doesn't have to promise something else, which I'm going to come back in a second because it's related to a notion of distributed consistency. Okay, so there is no transaction ordering overall. And commit, it's permanent. I'm sorry. This is kind of built into the system, right? If I set abort, no change is reflected in the state. It's not so much that no change is reflected in the state. The system looks to all participants as if no change is reflected in the state. What you do is your business. The question is, how does the participants see the system? But when you say commit, that's a very strong notion, because that essentially means no matter what happens, power goes down, whatever else happens, the transaction is still considered to be committed afterwards, right? Now, when you're talking about a distributed version of this, and I want to start talking about that, things start to become complicated, okay? Because I now have multiple such sites. You see, when I run in a multi-threaded program, hey, at least if I promise the user commit, it's somewhere in the shared memory, so presumably you could check to see that something is committed. So it might not be quite so bad, even though it's bad for other reasons. When it comes to distributed systems, for example, you have replication into the game. We talked about this. Replication is crucial. I replicate the database, and I can do replication for many reasons. Right? By the way, replication can even be something that's has nothing to do with geography. I have a large, extremely important e-commerce database server. I need to replicate to keep a hot spare in case this one goes down. I have to put this one back within a few seconds to continue doing the transactions, because otherwise people are going to be very upset. Right? Imagine, for example, that the Visa servers are down. The whole world cannot get food. Right? You say, but I have no cash. Things like this happen. It's a complete disaster. Right? So if you're replicating the database, the commit or the abort becomes much, much, much trickier. Why? Because if for any reason any of the participants has to abort, everybody has to abort. If for any reason, you cannot then say that you committed unless all the participants agree that that transaction is committed. Okay? You cannot have a replica thinking that the transaction committed and a replica thinking that the transaction aborted, because we don't have transactions then. It becomes impossible to program. Okay? Now, you see why you might, in fact, investigate other notions of consistency, because if you're doing this kind of extremely strong transactional consistency that we need to insist more on, it's potentially going to be extremely hard to enforce. Right? Eventual consistency, and I want to talk about them in parallel. Eventual consistency is exactly the opposite, in which you say, yeah, whatever. Eventually, if you do nothing in the system, the change from one server will propagate to the other servers. If you keep on changing, there is no guarantee that it will ever get anywhere and converge in any way, shape, or form. But if you don't do anything and you let the system be, maybe within an hour, the changes are actually propagated. No notion of transactions whatsoever, no notion of sequencing of events. This is usually only a weak promise on individual items, right? So if somebody bought an item, eventually everybody's going to find out that they bought that item, whatever that means. Okay? Now, another problem with the transactions is the following. The system does not promise any sequence of running the transactions. Now, that's usually used in a big way on a single, possibly multi-core system or a tight system. Right? In order to do all kinds of tricks to speed up the transactional processing. For example, you could pick and bundle up together some small transactions, leave aside big transactions, do all kinds of things. So even though there is no promise that with respect to transactional ordering, you create a big issue if you run transactions in different orders on different machines. Because you could get inconsistent results even though each system is consistent itself. Right? So when you run transactions and you have to apply them against multiple sites in a distributed system, you have now a complication with respect to the consistency that has to do with the fact that you run independently on all of the machines. Right? And that's not necessarily something that you can get away with, and it's very hard. If you promise transactions, you better promise that everybody sees the same thing. Right? There is very little value in running transactions locally but not having global transactions, because it can get actually very tricky to know what happened. You might as well just say give up everything and go to eventual consistency, which is going to be orders of magnitude faster in the first place. Okay? So in principle, if you apply transactions in a certain order on one machine, you should apply them in the same order on all the machines in order to get exactly the same state. So not only you want a consistent state per site, which is going to be ensured by transactions in general, but you want the same consistent state per site. And this can actually be extremely, extremely tricky. You can try to bend it a little bit, but it's sometimes hard to foresee exactly how that's going to haunt you back in the future. Also, it's not quite clear what it means to have the same state on all the machines, okay? Because you have to ask yourself the question, what is state? So if I say same, that means there is an equality operator there, right? So what's the equality operator between states? That's the trick. By the way, equality is a nasty notion in general in all the high-level programming languages, right? In C, there is the ultimate way to say if things are the same. It's compare bits. You say, hey, it's a pool of bits, compare the bits. Any small difference in the bits is a disaster, right? Even in C, you can't really do that because, you see, the smallest fluctuation in how the multithreading goes, you use, for example, the placement of data structures in memory in different way because you called malloc in a different order, right? You don't have anymore a one-to-one match between the bits. And you can't expect that. You say, hey, that's stupid. Why would I look at the bits in memory of the true system? So the goal is really not to have exactly the same image on all the machines. That would be devastatingly bad, okay? The goal is to have some sort of a high-level notion of same state, right? So for example, you say at the logical level, the value of every item involved, if I can do only reads and writes on those items, is essentially the same. I don't quite care how they are organized in memory. They can have very different organization, but they have the same value. Nevertheless, this ends up being quite a difficult problem. So what we need to do is start going through various notions of consistency and see how can we deal with it, okay? Again, the big prize is going to be, the ultimate prize is going to be this transactional processing and something called distributed transactions, what's happening in here, in which we have this extremely strong promise, right? This is precisely what the credit card companies do. So, I mean, the reason they can afford to charge that 2.5%, right, is the fact that they offer this notion, extremely strong notion of transaction. And not even Amazon can escape that, right? So Amazon can play games with do we have the item or not have the item in various warehouses. It's somewhat equivalent to games that, for example, airplane companies are doing with people that fly. You always overbook because you can always offer $500 to the people in the plane and somebody's going to give up their seat for a room in the hotel and $500, right? It's the same thing with Amazon. Hey, we just send a nice email saying we don't have the item and we're going to try to get it or not to get it or whatever. But when it comes to financial transactions, you can't do that. So you have to do this, right? This is why Visa invested and MasterCard, and this is why you don't have so many, by the way. You only have 4 or 5 of them internationally, right? This is why they can afford to charge whatever they afford to charge because they offer this kind of a service, right? So you will need, for those financial services, distributed transactions. Okay. Now, the crucial question for you as a developer is going to be, where do I want to be in the spectrum of consistency? Right? Because if you really want that, you better put the enormous amounts of money that Visa puts in to keep up such a large system with distributed transactions alive. If you can play games with eventual consistency, then, hey, you can use the open source Cassandra and you're done because it has eventual consistency. It's, by the way, built by Amazon and open source. It's kind of what powers their engine, like Cassandra. We need to talk about this separately. Okay. Now, usually, when it comes to these weaker notions of consistency, you have also a much weaker data structure support, right? Transactions can support these very complicated things because a transaction, you can say begin transaction, then do hundreds, thousands of things, and then end transaction. So you can have almost arbitrarily complex interaction between things. But when it comes to this kind of eventual consistency, usually the model, the data model is very simple. You only have objects that have some properties, and those are limited. And you cannot talk about how objects interact with each other. You have to consider the interaction of every object independently, right? And that can be a significant limiting factor in a particular application. Or it might not. I mean, Amazon managed to get away with lots of things, right? So let's see some of these consistency notions and start weaving some sort of a story here. Now, one crucial notion of consistency, and maybe arguably this is the only notion that matters, is data-centric consistency models, right? So, I mean, arguably, everything should be about data. Because what would you do with systems if not data, right, in the end? Right? Why would you bother to put so many computers around just to see if they can tick together, right? So it's almost always about some sort of data and some sort of things you want to do with the data. Look things up, change things, stuff like that. So no wonder a lot of the consistency models are data-centric consistency models. That means you're consistent with respect to what you do with the data and the view you have on the data, local view versus global view, and things of this sort. Okay. And consistency, again, is deeply connected through replication with the notion that things are, in fact, persistent. Right? Persistent in the sense that you don't lose them. So you better not lose the things. And that includes power failure and so on. We're going to talk about specifically interesting tricks you can do if you can isolate physically systems, in which case you don't even have to write on hard drives, as long as you know for sure that not all of them are going to go down. I mean, if there is a national power failure, then all of them are going to go down. But if you have only local power failures, as long as some replica, it's still up and has things in memory, you're fine. So you don't necessarily need to write on the disk, but you have to promise you're not going to lose things. And the commit, it's related to don't lose things also. Okay. All right. Now, when it comes to consistency, and I want to start with some of these notions. When it comes to consistency in distributed systems, there is a lot of work in database systems on this kind of transactional processing. In distributed systems, they try to come up with all kinds of notion of consistency. Now, the weaker the notion of consistency, the better the chances to have a higher performance system. At least that's the hope. Again, eventual consistency is very, very weak and possibly very high performance. This kind of transactional processing is very strong, potentially not particularly high performance. Okay. Good. So continuous consistency is an interesting notion introduced in 2002 by Yu and Vadat, in which they basically say, you know what, we can provide some sort of a tuning parameter, and you can tune in any consistency you want. Now, before I even describe this, I want to describe this high level. Before I even describe this, it's worth pointing out that nobody really deploys this kind of consistency, right? So but it's an interesting exercise. So if you have this kind of tuning consistency, you're talking about what kind of errors you could tolerate. Ultimately, this is about what could you tolerate, what errors you could tolerate. Eventual consistency means you're not going to bet that two servers have the same value unless the value did not get touched for an hour, let's say, if the consistency model says that changes get propagated within the hour. Okay. So the idea these guys came up with is the fact that you somehow, for your specific application, can come up with measures of how wrong you can be, and then you build a consistency model around it and protocols that will enforce that consistency model. Now, if you're talking about numbers, then there is a natural way to come up with some sort of a measure. For example, you can say, you know what, and this is the case here, right? You're only doing operations on numbers, right? The numbers have names like A and B. Right, so you have to specify what operations are in fact performed. And it's OK if the difference between states at multiple sites differs by at most, let's say, 1. Right? So we are only talking about integers. So you can make a mistake, but the difference can only be 1, let's say, which means you can have different values for the same item at different sites, but the variation, how much they can differ by, it's only this strict epsilon. Okay? Now, this is an interesting and intriguing notion of consistency. It's not quite clear how useful it would be. So imagine, for example, I would say, you know what, I'll run financial transactions for you, but you have to allow me to make mistakes in the financial transactions, and I'm going to make a mistake within $1. Of course, the trouble is, OK, within $1 for what? Per transaction? For the lifetime of the account? If it's $1 per the lifetime of the account, we might tolerate that. If it's $1 per transaction, it could be a disaster, right? How many of you have seen this movie? It's a classic movie. 1 second, let me remember. I think Office Space?
Yes.
So how many people saw Office Space? No, you have to see this. OK. So these guys, right. So they figured out that they can actually make a little bit of money by intercepting the program that does the financial transactions and simply chip off the leftovers beyond the decimal point, right? So they take the fraction of a cent, right? And because their system was processing quite a lot of things, they estimated that they're going to do about $1,000 a month or something like that. I don't remember the numbers. Anyway, they make their change to the system and so on. They come the next day, and they put aside some enormous amount of money, $1 million or something like that, because they made a mistake in where they were shaving things, and they were shaving dollars instead of fractions of a cent. And then lots of other stuff happens, which makes the movie extremely funny, right? But what I'm trying to say is, this kind of notion of consistencies are potentially very hard to control to say what would happen in the end. So it's kind of a nice, intriguing academic issue. Can I have some sort of OK, stay within an epsilon? But unless you have some other notions built on top of it, this could in fact be a disaster. So if I'm allowed to shave off $1, I can become rich extremely fast if I'm one of the guys that actually does the transaction. By the way, Visa does not make $1 on most of the transactions. They make only 30-something cents. By rounding up in the right way, with this kind of notion of rounding up, they could actually make a lot more money, right? Again, the trouble is, it's hard to extend the notion of what a little transaction, error in a little transaction would have, what influence that error will have over a lifespan of a number of these transactions, okay? And without that, nobody in his right mind is going to go and use a system like this. Nevertheless, users came up with an interesting notion. It's the notion of CONIT, which is the unit of consistency. You say, OK, so you want to be consistent with respect to what? This kind of small operations to a single item or something like that. And I try to see, is it possible to design such, protocols that only guarantee the within epsilon error, but they try to be as efficient as possible within that realm. Sure enough, nobody is particularly interested in using those protocols, right? But again, big uncertainty with respect to what do they do in the long run. Okay, intriguing notion. Their argument, though, is the following, that if you do this, by manipulating the epsilon, you, in principle, could tune in just how much paranoia you want in the consistency model, which means you could tune in the amount of penalty, performance penalty you're going to pay for it. Okay. It's, again, not clear if it's worth it or not worth it. Right? Remember when we talk about some of the distributed systems issues, for example, when we talked about, for example, group membership, leader election, we said, hey, if I have an algorithm that is not guaranteed to work correctly, but it works correctly with a high probability, if I make that probability 10 to the minus 40, for example, hey, that's going to be good enough. Now, if the epsilon could be made that small here, that would be nice. But it turns out that the dependency on the epsilon is quite bad for this algorithm. So even if you want to study something like this, the key question is, what's the savings in terms of performance with respect to the epsilon? Because the incentive would be, for example, to make the epsilon relatively small. So for example, I can make the epsilon 1 over 10,000, let's say, relative value. Even that's not going to be enough in the financial transactions, right? And then the question is, do you even save anything versus transactions or things of this sort? And probably the answer would be no. Okay? So again, this notion of CONIT, intriguing, but I don't really see this deployed. It's what is the smallest, if you want, it's the equivalent of atomic operation. What's the smallest state, the smallest substate for which I can talk about some notion of consistency, but not a global consistency, right? So it's equivalent to, instead of saying the states overall are consistent, parts of the substates are consistent, right? It's a much more confined notion, which means you have more freedom. Okay. Now, sequential consistency is something that is much better studied. By the way, the previous one is basically a lone paper in some conference that published some theoretical results, but it's not something widely deployed and widely tried. Sequential consistency is of a completely different kind of animal. Okay. So the notion of sequential consistency, in fact, the initial notion comes from database systems. Right? And it has to do with the core question of, even on a system that has concurrency only, but no distributed, right? What does it mean to correctly run transactions? And that has to do with what exactly is a transaction and what are you promising. So it's not only that you can roll back the transaction and commit, but it's something called acid properties, right? Namely, that every transaction runs independently of the other transactions. So in particular, until a transaction commits, nobody else sees the changes made by the transaction, right? At least you can simulate that. In case you abort, nobody will ever see the changes, but if you commit, only after the commit you should be able to see the changes. Okay. Actually, no, there is right, sorry. So even when you're talking only about, again, multi-threaded systems in which you just have concurrency, you have to be very careful about how you define consistency on that system. Okay? And this is where the first notion of sequential consistency came into play. Okay? So one kind of promise you can make is that the state of the system, if you run transactions, you're going to run transactions in parallel, but the state of the system is going to be equivalent to one of the sequential executions of the transactions. Remember, when you say transactions, at least on a single system, you make no promise about any order in which transactions run, right? So you can weaken things a little bit, but still make a fairly strong promise. Namely, the state of the system is equivalent to some kind of a sequential execution, but not necessarily in any order that the user provided. When let's say 10, so you have transactions from 1 to 100, but if the state is identical to the state in which the execution of T1, then T100, then T16, let's say, then T22, so on and so forth, executed, right? Then we essentially say that the state is equivalent to a serial execution, no particular serial execution. So, for example, how many ways, if I have 100 transactions, right? And if I can pick the order, if I can manipulate the order in which they run, how many different, potentially different states am I going to end up with? Well, it's 100 factorial, whatever that is, right? All possible orderings of 100 transactions. Now, the promise you make is that the system is going to look as if the transactions don't overlap, even if though in fact they overlap. But you still have a lot of possible correct orderings, namely 100 factorial. So then you can come up with a very strong notion. I'm not going to go into this. I go usually in the database class, right? In which you say any parallel execution of transactions, right, is, I'm sorry. When it comes to consistency, let's backpedal a little bit. I mean, a core issue when it comes to this kind of things is how can you theoretically come up with some sort of a characterization? So usually how does theory work? You come up with some definition and then you prove that if something defined in that way, you say the things defined in that way have the following property, proof, and then you go and you prove that. Okay? So when it comes to consistency, to prove that a system is consistent, you have to first come up with a notion of consistency. But that's some sort of a notion of equivalence, right? You basically say a system is consistent if two things are equivalent, but the key question is what kind of things could be equivalent, right? So you can come up with an extremely strict notion, which I implied before. You say the execution is, for example, at multiple sites, execution is consistent if everybody ends up with the same bits in memory. Now that's, if you end up with the same bits in memory, at least they are at least consistent with each other. They all have the same bits in memory. But that's a devastatingly bad notion, because I have to make sure that I do exactly the same tiny, tiny things that don't even matter in the end to all the multiple sites, right? So coming up with more efficient consistency protocols is tied to the notion of coming up with notions of equivalence from the point of consistency that give up more and more and more and more, okay? Now, one such notion is this serializable schedules. So serializable schedule refers to the following kind of notion is the state of the system, it's equivalent, I mean it's equivalent, is the same state from the point of view of the values of the items, right? So the state of the system is the same as one of the possible serial executions of the transactions. So if you have 100 transactions, you have 100 factorial. So no matter what I end up in memory with, when I run my, so I'm going to say my particular execution of the transactions is consistent if it's equivalent to one of the 100 factorial serial executions of the transaction. Equivalence in that circumstance is defined as all the items have the same value in both. Okay? Now, this is a very nice theoretical notion of consistency, but it's highly impractical to check, right? I mean, to start with, you have 100 factorial possible states. I mean, first of all, to come up with each of the states, it's hard. You have to run the transactions, right? You cannot go and, in fact, check by creating these states that the states are equivalent. So these notions, these equivalence notions, right? So two executions are consistent if they I'm sorry, if I'm sorry. A parallel execution is consistent if it's equivalent to a serial execution. One of the possible serial executions cannot be enforced by creating things. The trick theoretically is to show that certain protocols will enforce this property. And these are some of the core big results in the area. For example, in databases, right, they prove that, for example, two-phase locking, which I'm not going to go into, they basically prove two-phase locking enforces serializable schedule. Okay? This is theory at its best, if you want. The same kind of thing has to be done there, even with this kind of different kinds of consistencies. You say, if you apply this protocol, you cannot have an error larger than an epsilon, if that's the continuous consistency model that you're actually using. Doing these proofs turns out to be very, very tricky. Okay? What I want you to understand is that a lot of these notions are too harsh. So even in databases, for example, serializable schedule, hey, that sounds good. But you might want to have weaker notions. For example, what's not clear at all is that it's worth it because I might have extremely diverse transactions that don't even talk about the same items. For example, when I do my financial transactions, why should I be concerned about transactions that somebody in Australia does? I mean, most of the time, I don't interfere at all with those guys. So an interesting idea would be to allow a lot more overlapping, a lot weaker conditions, especially if there is no chance to interact between transactions. But how do you know if there is no chance to interact? Right? Now, I want you to keep in mind a specific connection, and we have to make that connection, right? With the notion of ordering. This is ultimately even related a little bit to clocks and global clocks, which could be used to enforce this kind of consistencies, right? I mean, think about the global clock. If you would have a global clock, you could apply the following trick. You say, if I have a global clock that's coordinated on multiple sites, the moment you issue the transaction, I'm going to stamp it by the time. And I'm going to say everybody in the system anywhere has to run the transactions in increasing order of this time. Right? If that's the case, then you at least have an easier way on portions. You don't anymore care about serializable in general, but running them only in a particular serial order, which is the global clock order, if that's what you ended up doing. And you wouldn't even need to do communication between multiple sites to enforce the same order, right? Because you know that you had the global clock, is perfectly coordinated, everybody agrees on what time everything had, and then they can enforce their own notion of I sequence them in a certain order. We know that that's expensive, if not impossible, depending on how things actually go, right? So when we talked about multicast and about various types of multicast, right, the total order multicast, the causal order multicast, or other kinds of less organized multicast, they're deeply connected to this kind of consistency models and transactions. Because one way to make sure that you enforce a certain consistency model is, in fact, to use one of those multicast mechanisms. And almost for any kind of multicast, you're going to have a form of consistency to go with it. So the total order multicast is equivalent to a total ordering on the transactions, right? So you can use a total order multicast to, in fact, enforce a total ordering of the execution of the transactions, assuming that there is no parallelism on every site for the transaction. And I need to revisit that in a few minutes, right? And then that essentially is equivalent to agreeing on an order in which to run the transaction. So at every site, you run the transactions in that order. But that requires a totally ordered multicast, which we already argued is, in fact, quite inefficient. Another way to do it is to keep track of which transactions could interact with other transactions and to talk about causality, right? So you say, I care about the order of transactions, but only if they could interfere with each other. And in particular, if one of them puts something in memory, then that I have a causal relationship with another one that comes later. And then you could use potentially some sort of the causality multicast, right? That enforces causality, but not a total ordering. Okay? But you need to keep track of who could interfere with who, which means a lot more keeping track of. Global order, at least in principle, doesn't need much more than some sort of Lampert clock, and everybody agrees that we run things in a certain order. Okay? So all of these notions, right, you gain some and you lose some when you try to enforce them. They might be hard to enforce, but they're very convenient to use or things of this sort. Okay? So usually in databases, the notion is either serializable schedule or slightly weaker notions, but still much stronger than any kind of causal relationship. Right? And they usually are applied to a single site because of the concurrency. Now here is an interesting trend, and we need to revisit this in the future as well. Because multi-threading itself is a very hard problem, a new trend is to, and you need distribution anyway, because multi-threading can go up to a certain number of processors, and then you cannot scale beyond that. It's very hard, for example, to have a system with much more than 64 cores. It gets extremely expensive very fast. So why is by the way, did you ever wonder why 64? What's so magical about 64? Well, it's related to hardware, and actually specific hardware build right now. It turns out that AMD processors have multi-processor facilities built into them, is built in hardware. So you can put up to 4 chips that can talk to each other to deal with the memory. And there is a notion of consistency, by the way, at the level of the memory also, right? So it's consistency everywhere, in fact. The moment you put more than 4 of them, that hardwired mechanism does not work. You have to use very expensive chips that will glue together multiple such processors. And you have 4 chips. Each of them can have 16 processors, 16 cores right now, right? 16 times 4 is 64. Intel does not quite go to 64. I think the highest they can go is to 32 because they use a different protocol and they cannot glue so many things together. Okay? But what do you do beyond that? Well, you can give up completely on just going with multi-core and say we do distributed systems. But then an intriguing possibility pops up, namely, it might be too hard to take care of both of the multi-core and distributed systems at the same time. The code becomes very complex. And what you could do is, even though you have a machine with 32 cores, you could virtually partition it into 32 machines that have 1 core, and simply run a distributed algorithm both on these 32 pseudo machines and any other machines that are connected to them through networking, so that a distributed system is created. So that, in fact, significantly simplifies the problem on one machine, because to achieve a serializable schedule is trivial. Because you're going to run transactions one at a time. You don't have multiple cores. You run on 1 core. You have no reason to run multiple transactions at the same time if you only have 1 core, really. Okay? And then all the pressure is put on the distributed systems that now has much more participants, right? So I had 100 machines, for example, before. But now, since all of them can have 32 cores, really the number of participants is 100 times 32 is 3,200, and that's quite a lot, right? So this is an interesting kind of compromise when it comes to software design, and a lot of database companies tend to do this nowadays. Instead of treating powerful machines as a multi-threaded system, they virtualize them, treat them as much simpler machines, and use just this kind of distributed systems glue to put all those resources together. How much more time I have? About 10 minutes? Or all the, okay. All right? So in that way, you're simplifying the local problem, and you're just increasing the number of participants for the global problem. But essentially, you don't solve 3 problems. You solve only 2 problems, a local problem and a distributed problem, versus unithreaded problem, multi-threaded problem, distributed problem. Okay? All right. Now, okay. So let's see what else I have here. All right. So sequential consistency. I'm sorry. So when it comes to consistency, again, what matters is the reads and the writes, and that's really your only concern. And this is a methodology, again, created by the database people, right? They said, hey, we just express everything in terms of reads and writes. And then you can talk about so-called conflicts between the reads and the writes, right? If you have transactions that read and write completely different things, then you have no worries in the world. Yeah, they talk about completely different stuff. Okay, that's great. But if they read and write at least partially the same items, you have to be extremely concerned about in what order the reads and writes go. Okay? Now, it's worth pointing out the following. Namely, the reads never conflict with each other. It doesn't matter in what order you read. If nobody changes anything, and we are just reading, we have no worries in the world. Which essentially means that if you have systems in which you mostly read, you might have a much, much easier life, and you might even give up on some super strong notions of consistency just because the chance of a conflict is much smaller, okay? And not capitalizing on that, it's one of the big performance hogs in distributed systems in general, right? So this adds yet another dimension to the whole problem, namely, the mixture between reads and writes. How often do we read versus how often do we write, right? Can completely change what's acceptable and what's not so acceptable, either in terms of consistency, but also in terms of which algorithm we should use, right? So before we didn't quite have perfect solutions. Now if you add this to the mix, the spectrum of solutions, it widens much more, right? So you have a lot more choices to actually take in there. An intriguing kind of notion when it comes to consistency is the following, which is not at all captured in here, maybe a little bit through these awards, right? Namely, a sort of optimistic concurrency. So this is a technique that could work fantastically well when you have a lot more reads than writes. Namely, you could essentially say, you know what, I'm going to work under the assumption that there is no interference between multiple sites. Okay? And then what I'm going to do is I'm going to detect if such an interference happened. If it did happen, I'm going to have a drastic solution, for example, killing the entire transaction. So rather than try to come up with interleaving between transactions that are, for example, serializable, namely equivalent to a serial schedule, you say, forget about it. We run them independently, and then try to detect if they interfered. If they interfere, we kill completely the transaction and start again. Right? Now, the killing completely can be done by essentially not allowing a transaction to write to the real state, but it needs to write in a temporary state, which is private, and it will move from the temporary state to the final state only when it gets special approval. These are so-called optimistic algorithms that are based on some sort of validation. Okay? They tend to be newer in terms of when they were proposed in the literature, and tend to work orders of magnitude better than the old mechanisms to enforce consistency, as long as you have a large number of reads versus the writes. Actually, it doesn't even matter if you have a lot of reads and a lot of writes. The question is, what's the chance that the conflict actually happens? So let's think about, for example, small transactions, financial transactions for small individual people, right? It's extremely improbable that I'm going to have a conflict with you. I mean, most of the time, I'm not going to sell you anything or do anything. But even with another small company, right? I mean, what are the chances? For example, here's how a conflict could happen, right? If I use the same credit card from two different places, let's say, to buy from exactly the same company at roughly the same time within tiny amount of time, because if you don't have very careful transactions in there, you might mismanage the money, right? But so many things have to happen for a conflict to even show up. So in those kind of circumstances, this kind of optimistic concurrency, it's probably going to be perfect. All you want to do is build a mechanism that will detect if such a conflict got created, and if it did, you just do the transaction again, right? We don't know for sure, but this is very likely to be the kind of consistency and the kind of distributed transaction mechanism that Visa is using. Otherwise, they would go insane. Now, this is not going to be particularly good if you have two parties that have large transactions and they interleave their transactions when they're applying things, right? For example, I need to make 1 billion modifications to the database. You need to make 1 billion modifications to the database, and we are fighting over only 1 million items with large possibility to conflict. And it's going to be a complete disaster. But probably that's not going to work in the first place, and maybe we need to re-engineer the system and not allow such long-running transactions, right? So finding any such good property of a system, for example, will optimistic concurrency work? Is it possible to run, validate, right? So that's going to run in the kind of following stages. You do an attempt to run, and you validate. If you pass the validation, you're allowed to propagate your changes. You're guaranteed that nobody can validate until you finish your validation. They can run, do the work, but they cannot propagate their changes, right? The same kind of thing happens to some extent in the eventual consistency. You're doing changes locally, and you're propagating the changes. This might not be a big problem, right? If conflicts are not happening that often. Okay, so I want you to understand these things. So the trend really, when it comes to consistency and mechanisms to enforce consistency was, hey, let's dream up these extremely strong consistency models. Then they prove that it's a disaster if you enforce that. And then kept on weakening it, to a point where it's still reasonably realistic and it kind of works, but you have to do a lot less work to enforce that consistency model, right? It's still not clear at all, for example, how you do that validation, what happens there, and that's a database issue in here. These guys even gave up on any sort of validation. They just say, yeah, make sure you don't destroy the data structures, but that's all. Another way to get around this, and then I'm going to wrap this up, is to simply not allow everybody to write. To say, you know what, I'm going to have a home base for every single item, and only the home base can write. Everybody else can only read. And then it's just a matter of when a change got made here to propagate the change, but you're not allowed to change it here. So I can only have stale data, but I'm not going to have inconsistent writes, which create a lot more problems, right? That in itself could alleviate problems, as long as your application can tolerate these delays in propagation of the value. And eventual consistency, most of the implementations have some sort of a home base for the data as well, right? Now, you still want to replicate in case sites go down and so on. But those kind of tricks could help tremendously in improving the performance. Now, I want you to understand, this is crucial when it comes to consistency, that you cannot just blindly use one of these systems. You have to carefully look at what it promises and assess whether that's good enough for your application. If it's not, you're better moving higher up, getting close to transactional processing or something. And if it comes to financial data, you can't do this. Amazon is not using this for financial transactions. It's using this only for, we have the item, we don't have the item in the warehouse, right? If they introduce a law that says you cannot allow people to buy items you don't have, Amazon has to give this up and do a real transactional system. But no such law exists, and Amazon sends nice emails, okay? Anyway, I'm going to have a quiz for the high-level notions for the consistency, and I still want to cover recovery and other things. These are some of the core issues in distributed systems. We spend at least another week on this. Anyway, we have Thursday, another 1 hour lecture. And probably I'm going to spill it over. Sorry, no quiz yet. I'm going to talk Thursday about it. Okay. Focus on the project and get the number of peers you're simulating as close as possible to 100,000 or something. Do at least 10,000.